Right, shall we get started then? 4 minutes is enough, isn't it? Alright, so more lecture, more theory. We will do more problems and have more time for that later, but as I was just saying earlier, the first 2 weeks has to be quite lecture heavy because of planning of the Easter holiday and the coursework. It's just not possible otherwise. So this is one of the most important theory lectures of the whole module. So it's a bit theory, but we reuse these results over and over and over again. So understanding this lecture would be good. Polar coordinates. So have you seen polar coordinates before? I think you have, right? Have you? Some nods? Yeah, seen some of it. So we're just going to use it with vectors, which will probably be new, which should be new to you. I think it's new to you to use polar coordinates with vectors. So that's what the novelty is in terms of the maths. So we're going to use a coordinate system with a fixed axis and fixed origin. Not going to make our origin move around. That makes things complicated and led Einstein to general relativity. So we're going to measure the distance of the particle from the center as r and an angle from the x-axis as theta. I'll let you read this another time, but we use polar coordinates for so much things, but especially anything to do with where distance is important, an angle. So cameras, satellites, things around the Earth, but basically anything with a curve on it, really, as you're going to see in these lectures. We need to use the vector approach to deduce things, to fully, basically deduce everything. But I'm not going to be testing you on your ability to deduce things, okay? So here we go. This is one of the simplest motions we could possibly do, and also most important. Something's going around a circle. Okay, so there's a vector, r, that goes from the center to the position of the particle. Notice that the direction of the vector changes, but its length doesn't. And the particle's velocity, in this case it's just traveling at a constant velocity, is always kind of tangent to the curve, isn't it? We learned that in the last lesson. Nice visual, that, isn't it? It's quite difficult to get the V label to move around. I've got these cheat sheets on vectors. According to your department, they've told me you've all done vectors. But I've got the cheat sheet, it's in the folder lectures to help you remember any of these formulas. We'll be using some of these things. Again, I'm not going to evaluate you on your amazing ability to deduce vector things, but we need it to fully understand this. So here's the first bit. So we need to describe the circular motion. There's lots of ways to do this. I'm going to do this with a vector, r. It's bold because it's a vector. It's not just a number, it's two numbers. So it's this number, the distance from the center times the cosine omega t. So omega, you'll see, omega t, this together is actually equal to the angle. We'll get to that. And I, you've all seen I, haven't you? It's a vector, right? It's the vector 1, 0. It's a vector that points along the x-axis, 1, 0, and it has a length of 1. So when you say r is this thing times I, that's your width along the x-axis, really. That's this distance, this width here. And then this number here, r times sine omega t, times j is the vector that points straight up. It's the vector 0, 1. So this number times j is your height here. Did the microphone stop working? It did. Of course the microphone stopped working. Okay, no microphone. So in other words, x equals r cosine omega t and y equals r sine omega t. If r and omega are constant, then from the last lecture, which was like rectangular coordinates, we had that the velocity, the vx, the rate of change of x in time, is just dx dt. We can differentiate this, and we get this number here, and the same for y. I've already done the same steps for y. So this is assuming that r and omega are constant. What does it mean when r and omega are constant? Visually. It's this motion here, okay? This. If r is constant, the distance from the center doesn't change. If omega is constant, that means that the speed it's spinning is the same. So we're just deducing this one case as the first simplest case. So the beauty of using the vectors here is that just by differentiating r in time, you're going to get the Vx component's going to appear here, and the Vy component's going to appear here. Now, I've substituted theta to equal omega t here. I guess I should have done it earlier, maybe. So just by differentiating the whole vector, we get the vector of the velocity. And if we differentiate again, we get the acceleration vector. So it's very straightforward to differentiate the vector. I and j doesn't change, so you just differentiate these terms separately. In this case, we're looking at circular motion. R doesn't change in time, omega doesn't change. You get these nice simple formulas that are very easy to interpret. Okay. We're going to now rewrite this. That was for rectangular coordinates, I and j. I and j are not the most natural way to describe circular motion. So we're going to have to take a bit of a leap in the imagination now to use vectors which are aligned with a polar coordinate system. I'm going to call them ER and E theta. And you'll see how they fit with what we just did. So these are two new vectors. And they're super useful because ER always points from the origin to the particle. And we can see that from the previous, just from the way that we placed the position vector, cosine sine, cosine sine. It always points to the particle, ER, and it has a length of 1. You always want to use these kind of vectors that have length 1. And E theta, just as we deduced before, you get, for the velocity, you get a minus sign here and a positive cosine here. So that's why you got a minus sign here and a positive cosine here. It points always in the direction of where the particle is going if it's on a circular route. Well, yeah, if it's on a circular route. So what we're going to do is we're going to just rewrite what we just did in the previous slide, but instead of use I and j, we're going to use ER and E theta because it's going to lead to a lot of simplifications. I'd just like to repeat that this is one of the heaviest lectures in theory, okay? It's not going to be all like this. So now let's write the vector r. Instead of writing it in I and j, we're going to write it in terms of ER. If we remember, omega t is just theta, so I should have probably done that here, theta. So we can just rewrite this as r times these cosine I sine j, right? So r times cosine I sine j, well that is ER. So r just becomes the length r times the vector ER. We can do the same thing for the velocity and the acceleration, and it comes out really neat. It comes out neat because the ER and E theta represent kind of the motion more closely. So the velocity vector v, just by using the definition of E theta up here, we can rewrite it to be just r omega E theta. And then it becomes incredibly, it becomes natural, once you're used to working with this, that the magnitude of the velocity is just r omega. The reason is because the magnitude of E theta is just 1. So it becomes straight away clear that the magnitude of the velocity is r omega. And there's some really easy, neat ways to interpret that in radians. Same thing with the acceleration vector. You can rewrite it as just in terms of ER. So I have a slide showing that. I do, but I want to talk about it here a little bit. So if you've probably seen that before, centripetal force points towards the origin. Right, you call it centripetal? Centrifugal? Can't remember which one it is now. But when you're in a circular motion, your acceleration points towards the origin. You've just deduced it here. It comes out in 2 lines, really. You just differentiate the velocity, you just differentiate the vector r twice, and you rewrite it in terms of ER, and you can see that the acceleration points towards the origin. So a lot of people learn that as if it's some sort of rule, but it's a few steps to deduce it from basic principles. Okay, so here's a summary. So now, previous calculations, they were for circular motion. So when the distance from the origin is always the same, and you're going around the same rate. Now we're going to just allow this to be any kind of motion now. So this is now just this is why I called the slide is called polar coordinate system. This is just general polar coordinates now. We always use ER as the way we define it. It points from the origin to the particle. And if you differentiate ER, you can use the chain rule for cosine and sine and deduce that the derivative of ER is just theta dot times E theta. E theta, the vector that points sort of along the trajectory, that you can differentiate it again with the chain rule, so differentiate sine and cosine, and then rewrite it in terms of ER, and you get this here. And you get two really nice natural ways to interpret these derivatives as well. I.e. that the way that the vector that points to the particle, the way that it changed is a vector that's tangent to the route, tangent to the path, and the vector that points in the direction of the path, the way that it changes is always equal to a vector pointing to the origin or away from the origin. And in general, the particle, you can always write that the position of the particle is r times cosine theta I plus r sine theta j. So that's just using just the definition of cosine and sine. This always equals where the particle is. It doesn't matter for any motion. And you can rewrite that as little r, the magnitude of the vector r. So the r that's not bold, just a reminder, is the magnitude of this vector. It's showing here. R is this length here, from 0 to p. Okay. And then we say the particle has the polar coordinates r theta. We can do the same thing for acceleration and the velocity vector. So yeah, it's a bit heavy, this I suppose. We could do this very slowly, step by step, but I'm not going to be testing you on this, but I want to provide it for you if you want to see where everything comes from. We're almost over with the complicated bit, I promise, so hold on for a bit. So just to complete the story, the velocity vector is always the derivative of time of the position vector. That's true for any coordinate system. We're going to see other coordinate system, other things. It's always true. The position vector in polar coordinates, as we just saw, is the distance r times er. So if we differentiate this term, we're going to get the velocity vector. To differentiate this, we just use, even though er is a vector, we can just use the product rule. You differentiate the first times the second plus the first times the derivative of the second. And as we just saw above, the derivative of er, here it is, you can work out by using the chain rule for cosine and sine, remembering that theta depends on time as well. This derivative here becomes theta dot e theta, and you get this simple form. You can do the same thing again for the acceleration vector, use the product rule, calculate it, and you get these things here. These equations are super useful. You'll see that all these centripetal, centrifugal, strange forces all come from just these steps, okay? So if you want to, you can always go back to here to deduce them. Here's a summary slide. This is just summarizing what we've already done. I'm always using theta in radians. The velocity is always tangent to the path. The velocity vector, that's one thing that makes vectors really cool. They tell you something intuitive about what's going on. And we could rewrite the things we just deduced in the slide before, that the velocity vector is some component vr times er. We deduced that was r dot. Some component v theta times e theta. We deduced in the previous slide that's r theta. And same thing for the acceleration. We're going to look at these terms. We're going to be using them. So these equations here, these are the ones that we're going to actually need to use to solve problems. Okay, so I put them in big red boxes. The previous slides are nice. I love them. They teach you what things are going on, but you don't have to remember all those. So you're going to have to use these ones here. Okay. And then v, which is the magnitude of the velocity vector, is by definition, by Pythagoras, the square of vr plus the square of v theta square root, same thing for a. And this is a little summary of how to go from er to I and j. Okay? You don't necessarily, you could use this to solve some problems, but you don't have to, I don't think. Okay, so if we assume that r is constant, i.e. that the distance from your origin doesn't change, then if the distance doesn't change, the derivative of the distance is 0, and the double derivative of the distance is also 0. If you substitute these in the equations up here, you will rededuce circular motion. You have that Vr is 0, V theta is just r theta dot, AR is just the velocity, the acceleration vector only points towards the origin because A theta will be all 0. Well, sorry, for circular motion you need that the theta double dot is 0 as well. So it's not accelerating angular. It's not going faster and faster around. Okay. So just an illustration of the vector stuff. So on the left was the circular motion at constant angular speed. On the right is also circular motion, but the velocity is changing. So you can see that the acceleration vector no longer points towards the origin necessarily, right? It can change its direction, and it's all to do with if it's accelerating, of course, or not. Right, pick up the pace a bit, I think. Don't know what that's there for. That's not there. That's just the end of the lecture. So, okay, I'm going a little bit slow. Am I going too slow, too fast? Am I going too slow? Give me some nods if I am. Am I going too fast? Give me some nods if I am. Nice, thanks. Okay. So I'm saying this lecture is, these are the heaviest, among the heaviest of the whole course. Okay, so hold your breath. Right. This is just an application of what we just did. Okay, before we move on to doing an exercise together. It's just an application. Many people learn it as if it's a totally different thing, but it's exactly the same thing we just deduced. Blah, 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 blah. Okay. So, imagine you're driving a car. And we're going to be looking at understanding the forces that go on in something like this. You're going along a path, and you're able to measure the distance you traveled along that path. So right, when you're in your car, you know when you look at how far you've gone, it's how far you've traveled along this path, right? You may not realize you've gone up and down, but it's the total length of this string, right? It's not the distance in a straight line from O to the end. So you may have access to the distance you've traveled. You may know your velocity vector, your velocity vector, which is tangent, but you often don't know your acceleration vector. So this is just a kind of example of if you have a little machine, a little thing recording how fast it's going, how far it's gone. It doesn't know everything though. We're going to use what you do know and what you can measure to understand everything about this. And what we're going to do is we're going to use exactly the same equations from before. The way we're going to do this is that we're going to study the motion just at the point here. We're going to draw a big circle and say that approximately, when the car's passing through this point here, it's circular motion. It's following a circle. If you know what this radius is of curvature, and that's the way we design actually roads and rails, we give the radius of curvature. If you know this radius of this big circle, you know that you're basically along the circular, you're doing circular motion at this point. And we're going to describe that in terms of this origin C, and the distance from the origin we're going to use as rho. We could use r before we use the r vector, but it's a bit confusing to use the r vector because there's lots of different r. So we're going to use rho instead. So as a summary, we're doing in 2D. The position of the particle is defined by the distance along the curve. That's like what a car would be able to measure, what many machines would be able to measure. For different bits of the trajectory, we could, if we were given what is the circle which best matches it, we could describe the velocity and acceleration and everything at the point A in terms of circular motion, in terms of the equations we just did, if we know c and rho. And then at different points of the trajectory, we just have to know, oh, if we want to know the velocity and acceleration at B, someone has to tell us what is the radius of curvature and origin of the circle from there. And that tends to be the case. This is seeming a bit abstract now, but with examples it becomes quite concrete. And we're going to use polar coordinates, but really in this scenario people don't tend to call them polar coordinates, they call them normal tangent coordinates, but they're the same thing. You've got one vector pointing along the tangent, that's the e theta component, one along the normal, that's ER. The only difference is that the n switches direction. If you're dealing with anything in industry and construction and transport and infrastructure, n points towards the origin of the curve of the circle, where it doesn't necessarily for e theta. There's a little tiny difference. Okay, so to understand the motion and that of those points, you just use exactly the same equations we deduced. So here, I've put here the general equations. The first line is the general velocity of anything written in polar coordinates, no assumptions. Here is the general acceleration in polar coordinates, no assumptions. But now we are going to make an assumption. We're not making an assumption, we know that at the point A, if we're given the origin CA, if we're writing everything in terms of CA, at the point A and close to the point A, the distance doesn't change from CA. The distance of the car or particle from CA doesn't change. That's how we define this circle. Somebody went along, measured the circle in such a way that these things are zero, near the point A. Any questions on that? Is that a bit abstract? Yeah? What zero is the change in your distance, your particle distance from CA, which is your origin now. When you're going around close to this bit, can you see that when you're close to here, if you look at how far it is to CA, it doesn't change. Right? Get a ruler, measure the distance from here to here, it's the same as from here to here. And that is how in infrastructure these curvatures, that's how they're calculated, how the distance doesn't change. So when these two things are zero, the general equations of polar coordinates simplifies a lot. Everywhere you see r dot and r2 dot, it's just zero. So in a second line, you've just zeroed all those two terms. So here's the velocity vector. It only points along e theta. And then this could be plus or minus et. So this is just a small little detail, is that the tangent vector, that is supposed to be e theta, not en, sorry. That is e theta, not en, that's a mistake there. The tangent vector is plus or minus the e theta vector from before. E theta always points in the direction that theta is increasing, but et always points in the direction you're moving. They're not necessarily the same, so it's plus or minus. So I just swapped e theta for plus or minus et. This is supposed to be e theta. And then you see that this r theta dot from before is just the velocity vector times et. Same thing for the acceleration. You can just now you can rewrite this bit here. Now that you know that r theta dot is v, and we deduced that before, you can rewrite that as v squared over r. We've done that already. That's the centrifugal whatever force, and we get this extra term here. And we can rewrite this in terms of normal and tangent components. Why are we bothering? Why are we doing this? We've just learned e theta and er. Why are we bothering to do this? What's the point? Why could it be useful now to rewrite this in terms of normal and tangent? Because it's to do with the practicalities of when, if you're on a roadside, someone's going to give you the vector en pointing towards the origin of curvature. That's the way that it's going to be defined everywhere. And someone's going to say, that's the vector that points in direction of travel, et. So simply put, it's just practicality. Someone tends to give you those things, and so we rewrite it in terms of those things so that we can calculate everything. That's it. I think doing the problems will make things simpler. So this is just looking at those equations from before and making a little sense of them. This is still wrong. This is still should be e theta here. So the velocity vector, as always, is the derivative of the distance vector in time. And we've just shown that it equals this, it equals there, blah, blah, blah. This is just a summary now. So v is plus or minus r theta dot. So what did I say before? Yeah, that's what I did before, plus or minus. Yeah. Okay. E theta must be tangent to the path when the center of the system is CA. And we can define that we can see now that the velocity, the magnitude of the velocity, r theta dot, it should intuitively be the rate of change of your distance along the curve, right? So s is how far you've traveled along the curve. If your velocity is tangent, the derivative of the distance is going to be the velocity vector. So let me just see if I make that as simple as possible. No, I guess this is just intuitive, right? If it's from the I guess that's also from the definition of the derivative, really. If you're walking along a path and you're stuck to the path, no microphone I can walk around, then your velocity is just going to be the distance traveled. So s is the total distance traveled. If you differentiate the distance traveled in time, you're going to get your total velocity. It's not a vector. It's just how fast you're going. You've given it how much distance you've changed. It gives you how fast you're going. But with the vector approach, we deduce that in terms of polar coordinates, that's r theta dot, plus or minus. Moving to the acceleration, in the tangential direction, we intuitively expect the acceleration tangent direction to be the derivative of the velocity in time. Now the velocity is always tangent, so we're just taking the magnitude here. So the magnitude of the change of the magnitude of the velocity in time, we can deduce as this here. Does this match the tangential acceleration? It does. This intuitive idea matches our previous results. So it's saying that the tangent component is r theta dot squared. So we just go back and check that matches what we deduced in vectors. So intuitively, we can deduce that the acceleration in the tangent direction is r theta double dot. Let's go look at the vector thing. So here, in the vector thing, it says that at, the acceleration in the tangent component, is plus or minus r theta double dot. So we deduced that without giving any thought to the meaning or the physics. But if you think in terms of just paths, you can actually deduce this quite simply. Remember that r doesn't change when you're in relation to the origin. Okay. Blah, 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 blah. Okay. I think this is getting close to the end. And intuitively, from the circular motion, we may think that the normal acceleration, the component of the acceleration in the normal direction, is the same thing that we get for circular motion. It's that centrifugal, I can't remember if it's centrifugal, that force that points towards the origin, and the vector approach that we just deduced does show that that's true. Okay, this is just a summary. Your velocity change to total magnitude velocity change, the derivative of the amount of distance you've done over time, which equals this in polar coordinates. The magnitude of the acceleration is always the square of the components summed together, square root. That's Pythagoras. We deduce that the tangential acceleration is just this here, and the normal acceleration that here. So these are some of the equations which are most important to use for the problems. So the equations that you use are quite simple, okay? So I provide the kind of way to prove them and deduce them for those who like that sort of thing. But these are the ones we're going to use. That's the end of this theory. That's the end of the hardest theory, I think, of the whole module. We will be using this many times to help understand it. So we're not just going to move on and be like, yay, we've understood everything. So we're going to do a problem now for the next 20 minutes, 18 minutes. And just going to let you all work on this problem and try to use what we've learned for polar coordinates. And me and Aris, if whoever's met Aris, stand up and wave or something. and we'll come around and help you to do the problem. So here's the question. You've got a boom. It's standing, it's kind of fixed to the floor, and it's this whole arm is going to move around O. So like that, O's here, it's going to move around O. Okay. But at the same time, it's going to extend B from A. This is going to get longer. So it's changing its distance and it's changing its angle. So we're told what is the angle at a certain moment in time. The angle is 20 degrees. We're told at that same moment in time how fast the angle is changing and how fast the angle is accelerating. This boom driver is obviously a bit radical and is like just pulling all the levers at the same time. We're given the distance L at that moment in time, but we're also told how fast L is increasing and how fast it's accelerating. So the question is, determine the velocity and acceleration of the point B. It'd be good if you can do that in vectors, and it would be good if you also give them magnitude V and A. That's it. Have a try. Go back to the lecture. I wonder if I can put up the lecture at the same time. Maybe I can. And we'll come around and answer questions. Hello.
Hello. My only question is here.
Sorry?
Should we do it in radians?
I prefer to do it in degrees.
Okay. So it stays like this.
Oh, sorry, no, radians. Sorry, I meant to prefer
Radians.
radians. I prefer
Okay.
radians. Sorry. So my brain isn't working fully. I prefer radians.
Okay.
Let's leave this as sorry. Yeah, but they can do it however they want.
Sorry?
But they can choose.
Yeah.
There's more than one way to do things. Oh, wonderful. Is that going to work? Of course. No microphone, but giant noise appearing. Yeah, makes sense. Oh, no, you don't. Fine, fine. Of course it doesn't work. Right. Why is it now that making noise? Aha! No.
So
Okay, so
when it's connecting to the
dual screen
visualizer-
doesn't work.
Yes, when it's connecting to the visualizer, it doesn't
What's
work.
going on with this room? Oh my gosh, I need to use the visualizer now, so let's turn off that. Please don't make a noise. Okay, I only have a short time left, so I want to I just want to go through this problem. So we've got an origin O. You've got the arm of the boom. B. Oh, come off it. Is it not ironic? The microphone doesn't work, the speakers don't work, but you have a giant static noise. Okay, so here's the boom. This thing is staying fixed to the floor, right? You are given that this distance here, L, extends. So these are the kind of ways that, you know, the information that people give you about things that they're able to measure, and you're going to transform that into things from the equation. So we're given this distance is fixed, this doesn't change. This one here is 7 meters. And we're told that this point B, so if we redo this here, OA, B is going to extend, but also the angle is going to change as well. So it's going to go this way as well, because the angle here is going to increase. So we're given all these things. What is the actual velocity of the point B? It's important to know the velocity of the point B. It's a huge weight. If it rams into something, the amount of destruction it will create is based on its velocity. And the difficulty to control it is based on the acceleration vector. Okay, so hopefully from the lecture, you could see that this distance here, the whole distance from the origin, that's always the R, not bold R. If you want the vector is always, so I'm going to do a little underline for the vector to make it different from the little r, is the distance r times the vector er. So that's the vector pointing from O all the way to B. From O all the way to B, that is your position vector. Right, so we're given that theta is 20 degrees, which we can convert. I prefer radians. So I'm going to convert it to radians, which is pi over 180. And I'm going to do the same thing for theta dot. And theta 2 dots. As I said, this boom driver is quite adventurous, changing everything at the same time. Right, just make sure I get the calculations right. Okay, so that's the position vector. If we differentiate r in time, that's just the length r. We know that r is 7 plus L. So if you differentiate r in time, that's just L dot. Oh, come off it. R double dot is L double dot, and we're given what those are. So if we then go to the equations from the lecture, we have that the vector r dot, which is the velocity vector, so it's going to be something like this. Oh, actually, no, it's got to be, yeah, it's something like this. It doesn't point along just this vector here because this distance is changing. Okay, so we were given from the lecture that that is your velocity vector, and that is equal to r dot er theta dot e theta. You don't need to rededuce this to do the question, but I think it's nice to rededuce it when you're kind of thinking about what things mean. And that means that the velocity, the total velocity, this is the magnitude of the velocity vector, is the square of these components summed together, isn't it? Square root. Okay, so that's the velocity vector. If you want to know the size of a vector, you take the first component squared plus the second component squared, and then take the square root. ER and E theta do not come into it. And this is from vectors. So if you want to revise vectors, the magnitude of a vector is the square of its components. When these two basis vectors, when their size is 1, and they are orthogonal to each other. So this is just a revision. If you want to do the full vector shebang, it's when you know this is true, and this is true for any basis vectors, then you have that the magnitude of the vector is the sum of the components. So here we just substitute now what this means in terms of L. It's just L squared plus R. Remember, R has got the 7 in there. It's got 7 plus L squared plus theta dot. Theta is just theta dot. We're giving it directly in the question. So you could put numbers now in here. Put numbers. Oh my god, my writing is terrible. Okay, exactly the same thing for the acceleration vector. It'd be nice if you could go back to the definition. You've got to differentiate the position vector twice. You've already done it once. You can look at this term and differentiate it again if you want to. So it would be the derivative of the first component times the second plus the first component times the derivative of the second. What was the derivative of ER? What was the derivative of ER? Was it E theta? I think it's E theta. We deduced that in the first slides, so good to go back to it. I think it was E theta, yeah, I'm pretty sure. Now we can do the same thing here. But there's 3 things here, so you're going to use the product rule over 3 things. Right, it takes you a bit longer. It's like R dot theta dot E theta plus R without differentiating theta double dot E theta plus R theta dot derivative of E theta dot. Where this here was just minus ER. Okay, I'm just rededucing things. It's not necessary. I just love it, and I think it helps understand things. but you're given that the result of this already from the lecture was in compact form this here times ER. Let's just check I got that right. Square somewhere. ER plus 2R dot theta dot E theta. And that means that the magnitude of the acceleration, again, for any vector, the magnitude of the acceleration is the square of the first component plus the square of the second component. So you could just replace all this with the L square square root. Whoops. Again, you've got to put the right numbers in here. But I fully trust that you're all able to put the right numbers in, and we're already 4 minutes over. So, yes? Why what, sorry? Which line, above or below this one? Below. I placed what with what? R with L? That's wrong, you're right. This here. This here shouldn't be L, is that what you're saying? Sorry, this is L plus 7. Sorry, I rushed that. That's R, right? R is not L. R is L plus 7. So we also made the mistake here as well. This should also be L plus 7. Sorry, a bit in a rush. The lecture slides are correct though. That's the only difference, I think. Yeah, let me just check that. Yeah, okay. Free to go. No idea how to stop that noise.
Hey, I've got a question.
Yes.
If ER is that, what is it in cosine stuff? Because I only know the ER derivative. What is ER by itself?
What is it by itself?
Yeah.
It's a vector. What do
No,
you mean, sorry?
No, I mean, like, ER
Sorry.
derivative is that.
Yeah,
What's ER?
it's just this. That's it. That's the only thing it is.
So you don't need to know that. There's no that type of version. There's no polar version of it.
No?
So you can only get polar versions of the derivative.
It's a very interesting question, yeah. When you differentiate, they relate to each other. But by themselves,
They don't.
they don't. And actually, the way we learn to do these things is we don't write them necessarily in rectangular coordinates. This is writing it in terms of another coordinate system.
Oh, so you just keep it as ER.
Just a yarn.
But then you can never do calculations with this one.
It's a very good question, you know. You can, using this here.
Okay. But
Or
it's
you
the-
can just forget Cartesian coordinates and just know that it's always the vector in the direction away from the origin.
the direction.
The
What?
it's a vector pointing away from the origin.
Oh, okay. And then
We
what's
have it in the lecture slides too.
Yeah, but it's just that, I don't know, this is like more step by step, and I assume that one I'm gonna get a bit.
Okay, sure. Yeah, of course. You're welcome to take what you.
What's E theta, like in terms of, wait, E theta will be the tangent.
Yes. Yeah, tangent is a little vector pointing along the tangent.
But isn't the vector the tangent to a path?
Sorry?
Isn't V the tangent to a path?
Yeah, so this is tangent to the circle.
Okay.
It's
So
not
only
always
to the path.
tangent to the path. In the normal tangent coordinate, I think it was because we chose that the car was doing a circular motion around something.
Okay. That's
Yeah, sorry, it's a bit rushed today. Most lectures not too rushed. Can I ask some questions? Let me turn this off while.
It's alright.
Sorry, this section was a little confusing for me.